Hello everyone and welcome! My name is Cheyenne Footracer. I am a graduate student in the Civil and Environmental Engineering program working closely under Dr. Zahi Cad. Thank you for listening in on my presentation today. I will be presenting on autonomous desalination by closed circuit reverse osmosis / nanofiltration powered by solar energy, and specifically we are working on this technology for the Navajo Nation. The Navajo Nation is an indigenous tribe located mostly in Arizona as well as in parts of New Mexico and Utah. So why does my community need this technology? Well, in our case and in other similar cases that follow the same physical layout, the Navajo Nation community is scattered, rural, and remote, thereby making it very difficult to construct sufficient water and energy infrastructure for all the homes in the area. It will take a lot of money and time to do so, and due to surface water shortages from climate change and unjustified water rights, a majority of the Navajo population relies on traveling miles to buy bottled water and or capture groundwater. And most of these groundwater sources tend to be unregulated, high in total dissolved solids, and depending on the location, high in arsenic, uranium, radium, and lead. From extensive and previous research, it is evident desalination by NF and RO are the most appropriate water treatment techniques for the Navajo Nation's brackish groundwater, without radioactive material or arsenic. And this is because RO-NF can reject 95 to 97% of the total dissolved solids or minerals. RO-NF use spiral-wound semi-permeable membranes and under high pressure can separate the permeate, drinkable water from the brine, aka reject or concentrate. Therefore, solar photovoltaic will power the energy consumers in the process, which will be the high pressure pump, as well as controls, valves, and sensors you need to run the system autonomously. And typical pilot scale or field testing systems only recover about 20 to 80% of fresh water depending on the size and number of membranes, leaving behind a large volume of brine, which brings up the question of how are we going to treat and dispose of this concentrated volume? But as mentioned in the title, we are going to be operating RO-NF in CCD mode, or closed circuit desalination. It is a new approach to operating, and therefore we are not familiar with any previous CCD-RO cases tested under renewable energy, let alone solar PV. The difference is it is a semi-batch operation where we are continually bringing in a batch of water and slowly concentrating it during CC closed circuit mode, and when we reach a set point concentration or recovery, we then drain the highly concentrated brine during PF, plug flow mode, while also bringing in fresh batches of feed water. And these two processes will continue in this order, repeating itself again and again. Advantages to CCD-RO over traditional RO include reaching higher recovery, up to 95%, which allows you to use less membranes. Higher recovery also means less brine production. CCD limits fouling and scaling, which are common causes for membrane damage and replacement, and that is attributed to the uniform flux distribution across the membrane. Lastly, CCRO offers lower energy consumption because it takes less time and less cycles through the membrane to produce the same amount of permeate. Looking at our goals, we want to be sure to 1. Achieve high water recovery that will reduce brine volume and management from impaired brackish groundwater using CCD-RO. 2. Successfully integrate solar energy for this autonomous CCD-RO system. And 3. Ultimately demonstrate production of drinkable water for the Navajo Nation as well as for other rural and remote communities. Prior to running real-time experiments, it is important to understand the chemical relationship of your feed water. Therefore, I used OLI software to analyze scaling tendencies of compounds as water recovery increases. And so with this knowledge, we decided to implement ion exchange and a cartridge filter for removal of calcium and magnesium. Again, we are not yet looking at radioactive materials. Over the year, I ran CCD-RO bench scale experiments to determine its performance on the Navajo brackish groundwater without solar energy to begin with. I used NF90 and BW30 flat sheet membranes, with NF90 being a looser membrane, meaning it has lower salt rejection than the tighter pores in BW30. 2 of the same membranes were run in series inside 2 small cells, as you can see in the bottom left. I tested at 80, 90, and 95% recoveries at constant conditions. I tested with and without pretreatment of ion exchange and filter. I made and used a synthetic water solution to mimic the groundwater from a specific well located in Arizona. Therefore, I was also able to test with different concentrations from less to more challenging waters. Here is the specific energy consumption results from the NF90 membrane. Specific energy is important because it tells us how much energy is required to produce 1 meter cubed of water. We notice as recovery increases, specific energy also increases due to the higher concentration created. We also notice SAC with and without pretreatment are practically equal for 80 and 90% recoveries. However, looking at 95% recoveries without pretreatment in purple didn't last a whole 50 hours because it reached max pressure, which tells us pretreatment is very important for NF90. On the right is BW30. Immediately you see NF90 resulted in better specific energy for 80 and 90% recoveries. Again, SEC appears to not be affected by pretreatment at 80 and 90% recovery. I want to note that these graphs represent less challenging water, and I didn't run BW30 at 95% recovery because we wanted to see this recovery with more challenging water. Therefore, the red and green dots in the graph represent just that. Like all others, SEC increases over time with each peak, but after a certain point they remain steady. But for 90% recovery with pretreatment in red, it continued to increase in specific energy after about 35 hours rather than remain steady like the others. And 95% recovery with pretreatment didn't even complete one batch before reaching maximum pressure, telling us that additional pretreatment on top of the ion exchange and filter needs to be included for more challenging waters at this recovery. Not only is specific energy important, but the treated water quality is as well to confirm our technology and process works effectively and efficiently. Therefore, we measure the salt concentration through conductivity, and we can tell it increases as recovery increases. EPA standards regulate drinkable water at 500 milligrams per liter TDS, which is about 0.91 millisiemens per centimeter. You may think 95% recovery is therefore not allowable if we want to remain within drinking water standards. However, when you average each batch, it ends up being around 0.9 millisiemens per centimeter. Looking at cell 2, we see that it has slightly worse water quality, which is due to the cell configuration. When brine leaves the first cell, becoming the feed for cell 2, it is already more concentrated than the feed water entering cell 1. Therefore, cell 2 has a higher chance of scaling, damaging the membrane, and allowing more salts through. Looking at both cells, we notice pretreatment helps improve water conductivity and therefore quality. 80% goes from 0.7 without pretreatment to 0.9 millisiemens per centimeter without. Looking at BW30, we see great improvement in water quality. Remember, BW30 is a tighter membrane, so this makes sense. We notice water quality decreases when comparing the more challenging to the less challenging water. And BW30 cell 2 was slightly higher in conductivity than cell 1 and had a smaller increase in average conductivity from cell 1 to cell 2 than NF90 cell 1 to cell 2. In conclusion, Bench told us NF90 is better performing if you desire lower energy consumption, but BW30 gives better water quality. It will have to be a balance if one is chosen over the other. Previous pilot-scale experiments with solar PV were completed in 2018, where the regular RO system was able to mimic solar and wind energy. Using solar irradiance and wind speed data for the site in Arizona, the students were able to translate the two into pump voltage and then into a percentage of pump power that we now call hardware-in-the-loop solar profiles. Since we'll be using solar, I will only go over the solar results for a 7-hour operation. We can see the pump setting go up and down from 0 to 100% in orange, as if the sun is coming up or being covered by clouds. It's a direct relationship between the two. As the pump power setting increases, specific energy consumption also increases. Permeate conductivity, on the other hand, follows a more inverse relationship. At higher pump power percentage, when the sun is at its peak, we have more power to push clean water through and therefore have lower conductivity. From this study, we would like to use the same system but modify it to CCD and provide more realistic solar profiles that include nighttime mode to help us determine what may happen to water quality overnight. Looking ahead, I will be running conventional and CCD RO pilot scale experiments with more realistic solar profiles. I'll also have to explore energy recovery devices and techniques, as well as explore other options for pretreatment, especially for radioactive materials and silica. Because this isn't a zero liquid discharge process, we'll need to explore brine management options. And once we are ready to move forward, we can begin in-field testing and then ultimately implement this technology for the Navajo community. Last but not least, I would like to thank the following organizations for funding this research, as well as the additional support I have received from the CATH Research Group here at Mines. And that concludes the presentation. Thank you for your time and joining me today.